So anyway, this talk is on doing a statistical downscaling of the climate change projection, and the climate change projection, regionalization of climate change projection to Taiwan is the main task of the Team 2 in the TCCIP project. And I would talk about why do we need why do we need downscaling, and then why do we do statistical downscaling? Because we also do dynamic downscaling, but this part is focused on the statistical downscaling, and then the method we are using. And of course, I have presented the similar ideas using the CMIP5 data in previous workshop. So this is more of an update from this newer CMIP5 data. And also, since the user community are very concerned about the uncertainty associated with projection, so I will also try to quantify the uncertainty and the source of uncertainty using some of the standard technique and summarize in the end. So why do we need downscaling or regionalization? I think simply mainly because the need from the impact community, study community, and since we are not really living in a global mean climate, nobody really living in a global mean climate. And also, but in a way that right now this global climate model are not really designed to provide these regional informations. So, for example, here I'm showing you the typical result from the global model for the Taiwan area. If you compare to the observation on the right, of course, this type of more precipitation over the southwest is captured by the model, but certainly does not really give you the detail if user community want to make the impact assessment. And then, of course, but it's not fair to the GCM anyway, because they are not really designed to capture this detail that change due to the topography or landscape or the coastline and so on. So, so we have to do something. There are two standard ways of doing. One is using the dynamic downscaling. I think following two talks, we'll be focused on this part. We also do that, but this, as I said, this talk is more focused on statistical downscaling. The idea is quite simple. When you don't have a high enough resolution from this climate model, if you have a high enough resolution from the observation, you develop a transfer function and then try to come up with a higher resolution data. For the dynamic downscaling right now, the main approach or main project associated with it is the Codex project all over the place and try to resolve the problem. And the problem associated is, of course, it requires a large resource if you want to cover all the scenario, all the different TCM, RCM, climate sensitivities. And of course, through Codex is kind of distributed this resource to different agencies. That's a good thing, but still it's hard to handle. So the main reason really why do we do the statistical downscaling is we really want to attack, or at least being able to know this uncertainty associated with the scenario or the different model climate sensitivity. And And it's certainly relatively cheap to do this kind of exercise. But this provides something that maybe user community will be able to start to do something. So I'm starting from this scenario. I don't probably have to say again here for the CMIP5. Mainly these four RCT scenarios from 2.6 to 8.5. And typically, for the uncertainty from the global climate model, for example, if I look at the CMIP5 models, here I'm taking some of them, and looking at summertime rainfall change with RCP 8.5 scenario, you say that, of course, people look at the ensemble mean first, but always, if you look at the individual model, there are some of the signal that might be coherent among the model, but certainly there are a lot of difference from model, especially if you want to look into the regional, local, or even local details. And for the uncertainty assessment, we are doing just follow this Hawkins and Sutton's work by trying to look at a fraction of the total variance through this large data set and try to identify how much uncertainty is coming from the model, or how much coming from the scenario, and how much coming from the model internal variabilities. So typically for global models, that actually the scenario uncertainty can play an important role, where even for global mean precipitations average over 20 years, actually the main contribution is always this model uncertainty. So we would like to look into further, if you zoom into a region like near Taiwan, how those statistics, how that differ from this global mean analysis. And the approach for the statistical downscaling is also quite simple, using this bias correct spatial downscaling using some kind of quantile remapping. And in this approach, typically you have to first upscale or aggregate this high resolution observation data to GCM resolution and try to do the bias correction. And if there is a trend, then you have to move it first. That's a difficult part, but anyway, otherwise the CDF won't be really useful if there is a trend. But anyway, that's the approach. Then you correct the bias with CDF, and then doing a interpolation of these difference. And then after the downscaling, add a trend back. That's a typical thing you can do. So here is kind of example showing that typically if the model, the black line here, has a systematic bias compared to the observation, and you can also do this stratification with different months through the year, since sometimes the weather system in different seasons are not necessarily the same, but anyway, you can correct it through this, and typically, as I said, that the original model data is here. If you upscale the high resolution observation data on the right, and then you take the ratio of the two doing the interpolation, and then multiply back to the observation to get your downscale result. That's typically what we do. So the same approach as before, but just using the same data, this new data from CMIP5, including for the present climate, the historical run, and for the future climate, including all four different scenarios. And CMIP5, of course, include much more models compared to the CMIP3. But anyway, but also different center can perform these experiments differently in terms of whether they do or not necessarily all the model run all these four. So when you do the data for this probability or uncertainty assessment, these number of models may not be exactly the same, but we try to include as many models as possible. The observation data, we're actually using a two-stage approach. So first, we actually downscale to the quarter degrees using the Aphrodite data from Japan. And then since we, in TCCIP project, we developed this high resolution graded climate data over Taiwan compared to the Aphrodite data set. Of course, it gives you much more detail, especially if the impact people want to use, that should be certainly much helpful. So the two-stage, I probably shouldn't go through it again, but anyway, just try to explain that actually we do this to the quarter degree first, and then go do the same procedure again and get it into the 5 kilo resolution of the data. So as I try to show that, for example, this two-stage with these two different observation, and then these projection from the CMIP future climate for the different season precipitation change. And when you go to first stage of downscaling, or even the second, it's from a particular model, something like this. So basically some of the basic signal from a global model is still captured, but to give you some detail. So here is just the typical result that we got from this exercise. The RCP 8.5, the end of century scenario for the summertime surface area temperature change around Taiwan, down to 5 kilo resolution. Here, center is on sample mean. So individual model, you can look at like this. So there are some models that has relatively small, and some model more. But it's always that we want to provide some of this probability information based on this individual projection. So here is the thing we typically try to show to the user community first with the median value from all these models. So this is for different season and from different scenarios. So typically you will see that, as I said, at the end of the century, the scenario does dominate the warming signals, and the seasonal deviation just a little bit. And you can also look at compared to the median value, look into the 25% higher. So this third quarter of the model is definitely has the projection more than that. So some of the people doing the risk analysis does need some of this probability information, and also for the 75 percentile, if you want. And for the similar for the precipitation, and for the median the model projection also again into the end of the century with different scenario and the different season. But at this time, you as I say that this season, the future precipitation change that are more sensitive to which season you are looking at. So typically you will have the wetter summer season, but relatively dry for the winter, and that's pretty much consistent no matter which scenario you are looking into. although with less forcing, you typically also get a smaller signal. And again, if you are interested in different percentile, you can easily calculate from this PDF information. So information is should be rarely used. I always think that it's user community dependent, and so if you get a PDF, it's very easy to calculate the probability of exceedance, and so whatever problem you want, you can derive from this PDF. So as I trying to summarize here is this using the box risk curve plot and try to look at this summer versus winter, and also through the different scenarios in the whole distribution. Okay, in the end, as I would say that I would like to make some quantification for this uncertainty attribution. So in a way that I'm showing you here for the global mean surface air temperature and also the precipitation. If you take 20 years mean, which is typically tell user community the signal. So if you zoom into the area near Taiwan and look in the temperature uncertainty from the temperature, it's pretty much similar to the global picture. Although typically zoom into a local, it will always give you higher internal variability, but scenario uncertainty usually quite dominant when you go to the end of the century. But and for the precipitation, again, even zooming the local area, that model uncertainty is still quite dominant. The total uncertainty. Although, as I said, the internal variability, especially for rain, is even much more compared to the temperature, even if you do the 20-year mean. So I will summarize it here. So I think these probability projection based on this CMIP archive can really give us this probability information, and also provide some of this uncertainty information. And as I say, that this statistical approach is relatively simple alternative to the dynamic downscaling that probably show in later from 2 talk. And for the scenario, the uncertainty associated with different sources, that as I said, the scenario is actually for the temperature signal is usually quite dominant. Near the end of the century, of course, through a time initially they are not as important, but near the end of the century they are. But this scenario does not have a strong contribution to the precipitation change, even for a global mean precipitation. And models and uncertainty is the main reason for those rainfall, projected future rainfall change. And I think the internal variability, when you look into the regional or local, that we always has a much larger influence that one should be aware of. So I'll stop here. Thank you. So any question? Yeah, it's just a routine work. So, but one of the main mission from our project.
your approach is very straightforward and it looks very nice. My question is, do you consider the performance of the present prime? Do you consider equal?
No. Yes, I should say no, we didn't really consider that, or using some sort of weighting function to the performance. Yeah. So, yeah. Well, but the previous talk has shown some of the strategy you may be able to do. But I think the IPCC community is always say that unless you can find a clear signal as to the projection from a model is related to your model for performance. Otherwise, if you have a different model performance, whether you choose a good model or not, always give you the same uncertainty, then what's the point of doing the selection? That some people will argue. So I think a lot of people try to figure out whether we can find a model that do have some signal we can pin down when a better model can provide unique projection which is worse model cannot do, or at least not as good. But
I agree with your comment in global point of view that if we focus on the regional, it is some GCA in a very useful. So yes. I usually exclude such garbage GCA.
Yeah.
With weighting function. This is my
okay. Yeah. That's also very variable things to do. We do have some exercise on those, but well, performance metric, as the previous talk say, that usually you have to link to the particular phenomena, and then much more variable can be have to be assessed together in order to give you a better picture. So it's much more complex when you're choosing so it will be kind of target oriented, then you can do some of this exercise. But if you are looking at general things, then yeah, you can still do that, but unless you find, as I said, good linkage between the performance and the projection, otherwise.
I really had a very similar question. We use the same approaches as this for downscaling for hydrological modelling. Before we had UKCP in the UK, we used a very similar approach. But we did include some weighting on performance of precipitation, which we found quite helpful. But the other thing I just wanted to clarify, I didn't quite understand the benefits of the two-stage process and what the advantage of that was compared to going straight from the larger scale to the 5-kilometre scale.
Yeah, well, initially we just think that, well, you actually have to do a upscale when you do the correction. So if you kind of through a very large difference in terms of the spatial scale, originally we are just afraid that they will cause some problem. But we do compare when you do one stage or two stage. The difference is actually not that much. So either way we can do, but anyway, that's the current approach we are doing right now. But as I said, that we do try the one stage first. But you know, the one stage, the data is only coming from Taiwan. We don't have other place to really look into. So if we want to look into this approach at this to other area, we have to have this high resolution observation data that are available for downscaling.
Actually, I have a question about the temporal, actually, the downscaling. For example, the PCSD is based on monthly CMIP5 data, right?
Yes, it's stratified.
Yeah. So after bias correction, actually, how do you correct the daily data actually from the monthly? Actually, if you use the observation to create the daily relation, actually, even though we use a different kind of GCN, second derivation can be very similar to each other. So did you check that kind of thing?
No, actually, we haven't really attempted to do the daily data yet. There are obviously there will be even more problem is the daily data set, and some of people use the analog in addition to the simple bias correction. So it requires much more work. So at this stage, actually our team 3 doing their weather generator first through this exercise. We are not doing the daily. So,
well, I just have very quick question.
Okay.
Can you show this slide which demonstrate that Taiwan is in only one breed from the TCMIP? One of the very
introduction one.
Yes.
Well,
let's mention it. In this slide, if we look at the large figure on the left, we compare the color pattern from green to red to yellow to pink, green, yellow, pink, and then to green and blue. That pattern is the same as the 5 kilometer resolution. Is that by instance or?
Oh, you mean color selection? I'm not using exactly the same one, but I try to get a similar idea. Which part is more and which part is less. Try to use the color and so it's well not necessarily.
The tendencies are consistent.
Yes, that's what I say. So as I said, the global model can only do things at their resolution. So okay, we probably should start for the coffee break. Any announcement? Or just, so when will be the...
So the tea break will till 10:45. Please come back on time so we can continue the next session.